Hello everyone, I'm Wildberger. In the last video we talked about transposes. Now we're going to talk about inverses, which play a somewhat similar role. So, however, the inverse story is a little bit more constrained, at least the way we're going to present it. So we'll make a definition that a square, say n by n matrix A is invertible. That means that if there is an n by n matrix B, which will be called A inverse, such that A times B equals B times A equals the identity matrix. And I'll put I sub n there, meaning the n by n identity matrix. Okay, and in such a case, in this case, we say that B is an inverse of A. Okay, so let's do an example or two. So, for example, suppose that A is the 1 by 1 matrix with element 3. Okay, that's pretty simple. Then A inverse is the 1 by 1 matrix with element 1/3. Okay, and that's because if we multiply them in this order, we get the identity matrix, which is the matrix with just a 1. And also when we multiply them in this order, we get the identity matrix. Okay, in fact, any 1 by 1 matrix is invertible. Any 1 by 1 matrix is invertible unless it is the 0 matrix. That matrix is not invertible. Okay, how about a little bit less trivial example? Suppose that we have the matrix A, which is a 2 by 2 matrix. Let's say 2, 1, 3, 1. 2, 3, 1, 1. Can we find another matrix B, same size, so that A times B equals B times A is the 2 by 2 matrix? So we need to solve A times B equals B times A equals the identity matrix in the 2 by 2 case, which is that one there. Okay, so have a look at the following thing. Suppose we let B equals minus 1, 2, minus 3, minus 1. Okay, let me just write this down. In other words, minus 1, 3, 1, minus 2. Let's have a look at this matrix B. Okay, then A times B equals 2, 3, 1, 1, and minus 1, 3, 1, minus 2. Let's do the multiplication. 2 times minus 1 plus 3 times 1 is 1. Below it, 1 times minus 1 plus 1 times 1 is 0. Over in the top, 2 times 3 plus 3 times minus 2 is 0. And 1 times 3 plus 1 times minus 2 is 1. Hooray! That is the identity. But we also need to check the other way around. B times A. That's minus 1, 3, 1, minus 2. 2, 3, 1, 1. And what do we get there? So minus 2 plus 3 is 1. Below it, 2 minus 2 is 0. Then minus 3 plus 3 is 0. And 3 minus 2 is also 1. That works too. Okay, so therefore we conclude that A is invertible and B is an inverse to A. Okay, great. Now let's establish a proposition that gets rid of this indeterminacy of the inverses. The proposition is that if A is an invertible n by n matrix, then its inverse, A inverse, is unique. There's exactly one inverse, not more. So what does that involve? So that involves assuming that there are two possible inverses and then showing that they're actually the same. So suppose that both, say, B and C are inverses to A. What does that mean? It means that A times B equals B times A equals the n by n identity matrix. And it means that A times C equals C times A equals the n by n identity matrix. How can we use these two equations to deduce that B equals C? Well, then let's argue the following, right? Then let's take the first equation and multiply it on the left by C. So C times AB equals C times the identity matrix. But the identity matrix has the property that when you multiply it by any other matrix, you get the other matrix. So C times the identity matrix will be C. On the other hand, this C times AB is also, by associativity, CA times B. So by associativity of matrix multiplication. And what is C times A? Well, C times A up here is the identity matrix again. So that's I sub n B. And then the identity matrix times any other matrix on either side will be that other matrix. So we're getting B. So in this chain of equalities, we conclude that B equals C. So A inverse is in fact unique. So from now on, we don't have to talk about an inverse to A. If a matrix A is invertible, then it has a unique inverse. Sometimes it's useful to separate these notions of an inverse on the left and an inverse on the right. That's especially also useful when we try to generalize the idea of the inverse of a matrix to non-square matrices. Now that's a bit more advanced topic, which actually works best once you know some Maxwell theory. So we're not going to actually deal with that, but it's still nice to have a separate notion. So let's make some minor definitions. If A and B are n by n matrices, and A times B equals the identity matrix, then we'll say that B is a right inverse of A. And A is a left inverse of B. So we could then say that a matrix is invertible if it has a left inverse and it also has a right inverse, and those two are equal. Here's a little proposition that I'm going to leave to you, which follows very much along the lines of the result that we've already talked about, the proposition up here. The proposition is that if A is an n by n matrix with, say, left inverse B and right inverse C, then B equals C. So if we have both a left inverse and a right inverse, then they necessarily must be the same, in which case A is then invertible. Okay, so I might put that in brackets, in which case A is then invertible. Okay, so some properties of the inverse. Well, but I should probably do the general 2 by 2. Let me do that before. I've given you an example of a 2 by 2, a rather special case. Let me show you the kind of trick that was underlying here, because I kind of pulled this this inverse out of thin air. Probably you're wondering, well, how did I get that? Well, there's a little bit of a trick which is worth remembering in the 2 by 2 case. So the 2 by 2 case is relatively easy. It turns out that the higher dimensional cases get increasingly more complicated, okay? But the 2 by 2 case is still very manageable. We can almost write down an inverse automatically. So that rests on the following computation. Let's suppose we have a general 2 by 2 matrix A, B, C, D, okay? And I'm going to multiply this by this particular variant. We're going to interchange the elements on the diagonal. So instead of AD, we have DA. And we're going to negate the elements off the diagonal. Let's just have a look at this. Okay. So what is this? The top entry is AD minus BC. The one below it is CD minus CD. Okay. And then up here, A times minus B. That's minus AB plus AB. And then below that, minus BC plus AD, for a total of AD minus BC, 0, 0, AD minus BC. So this is a diagonal matrix. In fact, it's AD minus BC times the 2 by 2 identity matrix. So this is the equation that sort of shows you, when a matrix is invertible. So we can deduce from this that if AD minus BC does not equal 0, then the matrix A, let's call it A, B, C, D, is invertible. And its inverse is A inverse equals, okay, we have to divide by this factor AD minus BC, and then we look at the matrix D minus B minus CA. Actually, to be honest, I haven't quite demonstrated that. To really fully demonstrate that, I also need to show you that that we have a left inverse. So I've established that the matrix A has a right inverse, but I also need to check it on the left. So let's make that calculation. So also, let's take the same D minus B minus CA that we had before, and A, B, C, D, and let's multiply them in this order. Okay, top entry AD minus BC, good. Below it, minus AC plus AC, yeah, that's 0. Over there, DB minus BD, yes, that's 0. And minus BC plus AD, that's the same as AD minus BC. So yes, that actually is giving us both a left inverse and a right inverse. So that justifies this statement here. This is a little rule that you can happily memorize, okay? It's a very useful rule to memorize because it gives you a formula for the inverse of a general 2 by 2 matrix. Okay, what do? First of all, you need to check that this quantity AD minus BC is not 0. If it's 0, then this doesn't work because the calculations that we have done give us the 0 matrix, not the identity matrix. But if that quantity AD minus BC is not 0, then we can write down the inverse by doing this trick right here, taking the interchanging the diagonal elements and multiplying the off diagonal elements by -1, and then crucially dividing by this important quantity AD minus BC. Now, not to let the cat out of the bag, but this quantity, of course, has an important name. So definition: the determinant of the matrix A, B, C, D, that is this quantity AD minus BC. Okay, that's called a determinant. Determinant of this 2 by 2 of this 2 by 2 matrix. later on, in a short while, we're going to be talking about determinants more generally. But you can already see at this stage that there's a close connection between the determinant of this 2 by 2 matrix and its inverse. First of all, the question of whether it is invertible, that depends on the determinant not being 0. And then the actual formula for the inverse, the one here, that's start, that formula has the inverse prominently in it. We're actually dividing by the reciprocal of the determinant. And that makes it obvious that that better be non-zero, because if it's 0, then we're dividing by 0, which is not allowed. Okay. So that's actually an important kind of special case, that 2 by 2 thing. And probably you should now be thinking, well, what happens in the 3 by 3 case? Well, that's very interesting. How do you calculate the inverse of a 3 by 3 matrix? Well, it's a little bit trickier, and perhaps not surprisingly, it ends up connecting very closely with row reduction. But before we do that, I want to now just give you some general properties of inverses. Okay, so properties of inverses. Maybe one. If the inverse of A equals B, then the inverse of B equals A. Right? Because what does it mean for A inverse to be equal to B? It means that AB equals BA equals the identity matrix of the right size. Well, that's symmetrical. Okay, that's symmetrical in A and B. So if the inverse of A is B, then the inverse of B is A. And another way of saying this is that if you take the inverse of A, and then you take the inverse of that, well, then you're getting A. And that's kind of pleasant because that correlates with the usual way exponents work. Well, another property is that if A is, say, n by n invertible matrix, then the inverse, okay, then let's say, then for any lambda not equal 0, lambda A is also invertible. Okay, so if you multiply a matrix by a scalar, and I remind you that means that you multiply all of the elements directly by that scalar, then as long as that scalar is non-zero, you're getting also an invertible matrix. And what is the inverse of lambda A? The inverse of lambda A is going to be 1 over lambda times the inverse of A. That's how inverses act with regard to scalar multiplication. How about with respect to addition? Well, for that we have to be more careful, so I'm going to note just to make sure that you don't think that inverses behave well with respect to addition. So note that A plus B, if you have two matrices and you want to take their inverse of the sum, this is in general not equal to like A inverse plus B inverse, okay? So in general, that's not to say that you couldn't cook up a matrix or two that have this property, but in general, inverses of sums is more complicated. That's the same the way it is with numbers. The inverse of 3 plus 5 is not the inverse of 3 plus the inverse of 5. Well, what about products? Okay, with ordinary numbers, if you take the reciprocal of AB, that's the same as the reciprocal of A times the reciprocal of B. Well, something happens like that, but we have to be a little bit careful, just the same way we were with transposes. So let's state it. If A and B are both n by n invertible matrices, so they each have an inverse, then A times B is also invertible. And we can give a formula for its inverse. So here's the formula. The inverse of A times B is the inverse of B times the inverse of A. That probably, I hope, reminds you of the rule for transposes, right? That's what happened with transposes. If we take the transpose of a product A, B, we get the product of the transpose of B times the transpose of A. So it's the same thing that's happening here. Let's give a little proof of this. So let's take A, B, okay? And let's multiply it by B inverse A inverse. I want to show that that's the identity. Okay, so what is that? Well, by associativity, we could write that as A times B inverse times A inverse, right? By the crucial property of associativity. But B times B inverse is the identity matrix. In this case, the n by n identity matrix, which we'll write like this. And we don't have to put brackets here because everything's associative, right? So we don't have to put brackets, around the A times IN or whatever. Now, however, A times IN is A. So this is the same as A times A inverse. Since A times the identity matrix is A. And then A times A inverse equals the identity matrix. Similarly, I'm going to leave it to you to check that we have a similar kind of formula if we do it in the other direction. If we start with B inverse A inverse on the left and multiply by AB, then we also get the identity matrix. So this is showing us that the matrix AB has a right inverse and it has a left inverse. Therefore, those two are the same. In fact, we see that they're the same. And so therefore, AB is invertible. Great. Okay, so there's a number of important things, kind of questions that we still need to address. One of them is, how do we calculate inverses of n by n matrices for n bigger than 2? That's a very important question. That question is pretty close to being at the heart of linear algebra, actually. Okay, that's probably the single, foundational computational question in linear algebra. That's so important. I'm going to write that down. That's the essential. Some people might think I'm exaggerating here, but not really much. The essential computation in linear algebra. How do you compute the inverse of a matrix? And we'll see that it's actually very closely connected with the problem of solving a system of linear equations, which I also said was an essential computation. So these two problems are really almost very parallel. And another kind of technical question, a little bit more subtle, is that if A is n by n and has, say, right inverse, say B, i.e., suppose we know that A times B is the identity matrix. How do we know that B times A is also the identity matrix? Is that true? So it is true. This is true. So it turns out that if we know that it has a right inverse, then it also has a left inverse, and conversely. This is true, but it's not obvious. It's not at all obvious. It's quite a subtle question. And we're going to have to examine our procedure of row reduction. We're going to have to sort of touch base with the actual computational algorithm of Gaussian elimination and its expression in terms of matrices in order to solve that. So that's quite an interesting question.